Welcome to section 3.1, where we're talking about the chain rule. In this section, we will see how to find the derivative of a composite function. We will learn about why we call the chain rule the outside-inside rule. We're going to find functions where we need to use the chain rule more than once. And finally, we'll generalize all of that knowledge into something we call the power chain rule. So let's get started with the derivative of a composite function. There's no new vocabulary here, but we are going to learn the chain rule, which is what this section is all about. So let's begin this way. I'm going to go to the white space at the bottom and make a couple of lists. So things that we know how to find a derivative of. So I'm going to do this. We know and we know. So we know how to find the derivative of a function such as, say, y equals the sine of x. We know it. It's cosine of x. We know how to find the derivative of a function, say, y equals x squared. But we don't, at this point, know how to find the derivative of a function like y equals the sine of x squared. Okay, another example. We know how to find the derivative of a function, say, the square root of x. We also know how to find the derivative of a function, say, x to the third, or x to the third, hey, like plus 1. But we don't know right now how to find the derivative of a function like y equals the square root of x to the third plus 1. So hopefully you see what we're doing here. Back to the example at the top, we can differentiate both sine of x and x squared minus 4, but how do we differentiate a composite function? So what we're talking about here are compositions of functions. C-O-M-P, compositions of functions. So you're probably used to seeing compositions as our fog and Goff problems, f of g of x, or write it as f of g of x. So this is the type of function that we are looking at today. The way we're going to derive it is with something called the chain rule, and it's one of the most widely used derivative rules in all of calculus. So let's move forward. The function y equals 6x minus 10 can be rewritten as 2 times the quantity, 3x minus 5. It's a composite of two functions. It's a composite of y equals 2 times u if u is defined as the function 3x minus 5. How are the derivatives of these three functions related? So let's begin with y equals 6x minus 10 and find the derivative with respect to its independent variable x. So dy dx in this case would just be 6. Derivative of 6x is 6. Derivative of negative 10 is 0. Let's move next to the function y equals 2u. So we have here dy du, the derivative of the function y with respect to its independent variable u is 2. Finally, let's move to the third function, which is u equals 3x minus 5. And this time du dx is 3. So how are all three of these function derivatives related? Well, you probably already see it. We have dy dx 6 might be equal to dy du 2 times du dx 3. So we can write that as 6 equals 2 times 3, or we might write it as dy dx equals dy du times du dx. So we might have the start of a rule here. Is this relationship, this dy dx equals dy du times du dx, is that a coincidence, or is that the way it will always be? So it turns out it's not just a coincidence. That's the basis for what we're going to call the chain rule and the way that we're going to differentiate composite functions from here on out. So if we think of this in terms of rates of change, it starts to make a little bit more sense. Down below, we have an example of multiple gears. When one turns, the second turns, and when the second turns, the third turns. And if we think about the derivatives in terms of the rates of change of these gears circling around, we can kind of get ourselves into this idea that dy dx equals dy du times du dx all the time. So here are 3 gears, and C makes Y turns, B makes U turns, and A makes X turns. So we can write that in terms of equations. A Y turn will be equal to however many turns U makes divided by 2, since Y is a bigger gear. So that would be U over 2. The little gear, U is going to make 3 times as many turns as the big gear, X, because X is going to have to spin 1 time, and that will spin U 3 times. So we have 3X there. So if we use substitution, then U can be placed in for U in the first equation, and we have Y is equal to 3U over 2. But if we look at their rates of change, dy du is equal to 1/2, and du dx is equal to 3. But what's dy du? Well, it's 3 over 2. So there we have it. Or actually, that's an x, and that's an x. dy dx is 3 over 2. 1/2 times 3 equals 3/2. So here's an example where we get to see it in action. We got a polynomial, y equals 9x to the 4th plus 6x squared plus 1, and that can be rewritten as 3x squared plus 1 quantity squared. It's a composite of a function, y equals u squared, and u equals 3x minus 1. So what we're looking at here is the 3x squared plus 1 is the u, and then we've got u squared as the function y. So we want to calculate the derivatives first as the polynomial y. So let's write y equals 9x to the 4th plus 6x squared plus 1 over again, and then find the derivative dy dx. So that's going to be, by the power rule, 36x to the 3rd plus 12x. There we have it. Now, if we write the function y equals u squared and differentiate, we'll have dy du, and by the power rule, that's 2u. Next, if we take the function u equals 3x squared plus 1 and differentiate, we'll have du dx equal to 6x. So is our conjecture from the previous 2 slides true? Is dy dx equal to dy du times du dx? Well, let's see. We have 36x cubed plus 12x. Our conjecture is that this is equal to dy du, which is 2u, times 6x, which is du dx. At this point, I really don't see it. We can say 2u times 6x is maybe 12ux. I'm okay with that. So what do we do with this extra variable of u? Well, I remember that from my original declarations, 3x squared plus 1 can be replaced with u. So we have 12 times 3x squared plus 1 times an x. We can distribute the 12, and that's 36. Let's try that again. That's 36x squared plus 12 times an x. And then if we distribute the x, guess what we have? 36x cubed plus 12x. It looks like our conjecture is right, that dy dx is equal to dy du times du dx. So we move forward. Here we're starting to build the chain rule for the first time. The derivative of the composite function, f of g of x, at x is the derivative of f at g of x times the derivative of g at x. So it's the derivative of f at g of x times the derivative of g at x. And what is this again? It is f of g of x prime. It's the derivative of f of g of x. And we have a graph down here at the bottom that shows how it works. That takes us to the chain rule. Here it is. If f is differentiable at the point u equals g of x, and g is differentiable at x, then the composite function f of g of x, which is written f parenthesis g parenthesis x, is differentiable at x, and that derivative is f prime of g of x times g prime of x. Or in Leibniz notation, which we've been doing on the previous slides, dy dx is equal to dy du times du dx, where dy du is evaluated at u. So in motion, here it is one more time. An object moves along the x-axis so that its position at any time t greater than or equal to 0 is given by x of t is cosine of t squared plus 1. Find the velocity of the object as a function of t. So first of all, this is a position function. We're finding the velocity, so we're looking at the derivative. So v of t is equal to x prime of t. Now we need to differentiate. Well, here's what we have. Cosine looks to me to be the f function, the one in which another function is inside of. And then the t squared plus 1 looks like the g. So this is f of g of t. So f is the cosine, g is the t squared plus 1. So by the chain rule, what we want to do is differentiate first the f function, the outermost function, and evaluate it at the innermost function. So we start with cosine, and the derivative of cosine is negative sine. We're going to evaluate negative sine at the inside function. So we leave the inside function alone. That's negative sine of t squared plus 1 times. Now we look at the innermost function, the t squared plus 1, which we've called g, and we take the derivative of it, and the derivative of t squared plus 1 is 2t. So altogether, this is negative 2t times the sine of t squared plus 1. And there we have it using the chain rule and finding the derivative of a composite function.